So, my dear student, here I welcome you in exercise 1.1 of the chapter number 1 real numbers. Right? What is the question 1? Use Euclid's division algorithm to find the SCF of. Okay, so we need to apply Euclid's division algorithm here. It's quite easy. Maybe some of you have studied these things in class 5th, 6th also. If you remember, then well and good. If you do not know, then also nothing to worry about. We are again here learning this thing. Now, what is the first step of Euclid's division algorithm says? The first step says out of two numbers, because this application is applicable, division algorithm is applicable for only two numbers. Okay, whenever two different numbers are given, first step says identify the greater number of the two. First step of the Euclid's division algorithm says identify the greater number out of these two. Of course, this is 2 to 5. Second step, consider the greatest number as dividend and the smaller number as divisor. So, my dear student, what is dividend here? Of course, the greatest number we will consider as dividend. So, dividend is equal to 2 to 5. Let's note down. What about divisor? The remaining means rest of the smaller number is known as divisor. So I need to mention the divisor is 135. Now third step says find the quotient and the remainder. So how to work out upon that? Just look at your screen. 2 to 5 is here. Now we are going to divide it with 135. As usual, you know, dear student, 135 to 270, which is greater than that. So we need to work out with 1. So here I need to mention 1. So if it will go with 1, then it will be 135. After subtracting, we will have here 12 minus 3, so it is coming 90. Now, what we have to say in the next step? The division algorithm says the next step is if the remainder is 0, if this is coming 0, then the divisor is required SCF. Whatever the divisor, that will be the SCF of this number. Clear? But here you can see, dear student, remainder is not 0. What is the remainder in the first step after dividing the bigger number with the smaller number? It is coming 90. So the process will go on. So next step says, what we have to do? Take the remainder as the new divisor. Now this remainder, it will become the new divisor and the divisor will become the new dividend. What was the divisor? 135. So I need to mention it here, 135. This will become the new dividend. Clear to you? All the steps which we have seen in the previous video, then you understood this thing nicely. 135, the step says this 135, this is the divisor will become the dividend for the next step. So let's begin with that again. As you know, when we divide 135 divided by 90, then it will work out with 1 only, because 90 to the 180 is bigger than 135. So here again it is not coming 0. Dear student, here you can see it is coming 45. So in such a case, what to do? Repeat the step 3, 4, 5. So what we have to do? Again, I need to mention whatever the here divisor, that will become dividend. So next step. What will be the next step? 45 to the 90. Now 45 to the 90. Now finally the remainder is 0. So how to justify the answer? What will be the answer? Of course, this divisor, where we are gaining remainder 0, so that will become the SCF. SCF of whom? SC of which two numbers? That is, first number is 135, another number is 225. The SCF of these two numbers, that is coming this number, that is 45. So this is the complete solution. We have solved this by Euclid's division algorithm. So dear students, exercise 1.1 is the question 1 and it's the second part. We are given the numbers are 196 and 38,220. As usual, you know, we need to mention what is dividend here. So dividend is the biggest number, so it will be 3823. Fine. What is divisor? Divisor will be the smallest number, so here it is 196. Fine. So my dear students, we are going to multiply. Now just look at your screen and think about that. The number which we are given here, 3820, that we are going to divide with 196. So how to apply? How to work out upon this thing? First, work out on the 3 digits. Okay, dear student? Work out on the 3 digit. As we know that 196 puja, it will be more than around 400. Okay, nearly 400. So we will work out upon that and we will have here 1. So here 196. What will be the subtraction? As we know, 12 minus 6. What will be the subtraction? It will become 8. Right? We know it will become 1, 1, 1, 8. That is 8. 12 minus 6. Okay. So it is 188. After subtracting 196 from 382, we will get 186. So what we have to do further? How to simplify? As we know that we need to divide it with this. Now we need to go with this. Just look at it here. 196 here. Just same number we are going with that. So reason behind that, we can work out somewhere. Somehow we can work out in this way here. I am showing you how to do. So dear student, here little bit correction I am doing. I am removing these 2 steps, and here what we have to do, actually we are given these digit in a 5 numbers and we are dividing it with 196. So first time when we divide it, we will get a 186 here. Now let me bring this 2 down. Okay. Now let's as a simple division. We are going to do as a simple division for this question. 196 9. 196 9, the answer is 1764. Right? So 12 minus 4 again 8. 15 minus 6 9, and of course here will be 0. So my dear student, what we have to work out here, one more 0 is here. So I am bringing this 0 down. Now 196 5 ja. If you multiply 196 5 ja, you will get 980. So my dear student, this is the simplification. So actually this is the divisible by this. So this number is already divisible by this number. So we can say here the SCF of these 2 numbers, 96, 38220, that is equal to 190. Clear to you? So this is our answer. So my dear student, here 867 into 55. These 2 numbers are given in the third. So what is the dividend? Of course the dividend will be the biggest number, that is 867, which we are going to divide it with. That is divisor. Divisor will be 255. Clear to you? So my dear student, here let's start solving that by applying Euclid's division algorithm. So here 867, we are going to divide it by 255. Okay. So So we know that 255 theta. What it will come? 5 theta, 2, 5 theta 15, 1 carry over 16, 8 theta 24, 8 theta 24, so it will come, what it will come? 7. Okay, so it is 765. Theta 6 and 1 carry over, so it is 7. 765. So if we subtract it, then what do we have here? 7 minus 5, it will be 2, 6 minus 6, 0, 8 minus 7 will be 4. Now dear student, as usual you know, in Euclid's division algorithm, we need to repeat this here 255, it will be written here, okay? And here 102 2ja we know, 102 ja, it will be 204. 255 minus 4, so it gives the result 1, and that is 51 is remainder. Still it is not coming 0. So what we have to do? I am repeating the same procedure as a step 3, 4, 5. Now again 51 2ja 102. So finally we have here remainder 0. So my dear students, we need to mention here the highest common factor of 867 and 255. What it is coming? What is the answer? The last divisor, that will become the SCF. The last divisor is 51, so SCF is 55. So this is the answer of this one. Now my dear student, before we proceed further in the exercise 1.1, first of all, I would like to explain you Euclid's division lemma here. Okay. Now what is that? Let's find out. So first of all, please note down when we are using this Euclid's division lemma. So it is a technique. Actually, this is a technique. This is a technique to find SCF of or GCD also, as you know, SCF highest common factor, or sometimes GCD greatest common result of two given positive integers. Of two given positive integers A and B, where A greater than B, by successive use of Euclid's division lemma. Euclid's division lemma. Keep this in mind. This technique here we are using. And now what is the statement? Let's work out on the statement of this lemma. Okay, this is why we are using, for which purpose we are using this technique. Let me explain you. Now what is the statement of Euclid's division lemma? Let's see. Now dear students, let's see the statement of Euclid's division lemma. Let A greater than B and apply Euclid's division lemma. And apply Euclid's division lemma. A and B. A and B for finding positive integers for finding positive integers Q and R such that A equal to, keep this in mind, dear students, A equal to BQ plus R, and condition is 0 less or equal to R less than B. Dear student, this is the condition for finding the Euclid's division lemma. Please keep this in mind, very important result. A equal to BQ plus R. This is very important. Under this condition, the value of remainder must be less than or greater than or equal to 0 and less than B. B is the another number. These A and B are two numbers. In that, 2 you know very well, that is quotient. And R is the remainder. Okay. Again, I am explaining A equal to BQ plus R. What is A? A is one of the number and B is another number. Out of these two numbers, remember dear student, the condition is A greater than B. Okay. And A equal to BQ plus R. Condition under 0 less than or equal to R less than B. R for remainder and B for another number. What is R? R must be greater than or equal to 0. And R must be less than the another number. This is the condition for Euclid's division lemma. Now dear student, here I am telling you the applications of Euclid's division lemma in finding property of numbers. Positive integers and their squares, cubes, etc. consist of certain interesting patterns and various properties, which can be proved by using Euclid's division lemma. Clear to you? Now some results. Let's discuss. If any positive integer is divided by 2, then the remainder be 0 or 1. If any positive integer is divided by 3, then the remainder be 0, 1 or 2. If any positive integer is divided by 4, then the remainder be 0, 1, 2 or 3. Now let's try to understand through the illustration and example given in the exercise 1.1. It's the question number 2 on your screen. So that any positive odd integers is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. This is the question. Let's start the sentence. Let A be any positive integer. Let A be any positive integer. A is a positive integer and B equal to, here we are given according to that, we are considering 6. Okay? B equal to 6. Then by Euclid's division lemma. Then by Euclid's division lemma. The lemma says, according to that, the value of A equal to 6. For instance, value of A, we are considering 6Q plus R. So, that we are already given A equal to 6Q plus 4. For some integer, that is, for some integer, Q greater than or equal to 0. And as we know in the Euclid's division lemma, the condition says here 0 less than or equal to R less than B. Here B, so B we have already taken 6. So here I need to mention this is 6. The possible remainder are, therefore, possible remainders are, therefore, possible remainders plural are 0, 1, 2, 3, 4, or 5. These are the possible remainders. Clear to you? These are the possible remainders 0, 1, 2, 3, 4, or 5. Let's see further. Once again, I am explaining here. A is the positive integer and B equal to, we are considering 6. Then Euclid's division lemma says A equal to 6Q plus R, because in the question we are given here 1, 3, 5. So for some integers Q greater than or equal to 0, and we know the condition 0 less than or equal to R less than B. B is here 6, so I am mentioning here 6. So the possible remainders can be 0, it can be 1, 2, 3, 4, or 5, because it must be less than 6. Okay, the remainder must be less than 6, so it will be up to 5, and 0 can be also possible. So these are the remainders, possible remainders for the given. So next is we need to mention that is what it indicates, that is A can be the value of A. A can be, it can be 6Q or 6Q plus 1 or 6Q plus 2 or 2 plus 3 or 6Q plus 1. Here, this is the question. Here, this is the question. Okay. The equal. These values are there for the A. So can we say if A equal, suppose value of A is 6, or value of A can be 6Q plus 2, or value of A can be 6Q plus 4, then we can say that A is an even integer. What will be the value of A? A can be an even integer. This is very important result. Also, an integer can be either even or odd. Integer can be either even or odd. Therefore, any odd integer is of the form of which form we will have? Of the form. Let's see which are the forms of it. We will write in the next. I'm explaining up to here. Here we know A can be, the possibility of A can be 6q or 6q plus 1 or 6q plus 2 or 6q plus 3 or 6q plus 5. Here, where q is the quotient. We know this very well. Now, E equal to 6q, suppose, or 6q plus 2 or 6q plus 4, leaving 1. Here we are dropping 6q plus 1, 6q plus 3 and 6q plus 5 we are dropping. Then A is an even integer. Yes. But as we know that integer can be either even, they can be even or odd also. So for any odd integer, it can be of the form. Which form they can be? Let's see. Any integer and odd integer. That's a difference. Any odd integer is of the form q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Please keep this in mind. Any odd integer is of the form. Which form we can have? It can be 6q plus 1, 6q plus 3 and 6q plus 5, where q is some integer. Here for even number we have seen, and this is for the odd. So this is the complete solution by applying Euclid's division lemma. Dear student, question number 3 on your screen. The question is, an army contingent of 616 members is to march behind an army band of 32 members in parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? This is the question. So, yes, here we have to find the maximum number of columns, right? So, maximum number of columns, how to find? By finding HCF of given two numbers. Which two numbers we are given? 616 and 13. Fine. So, dear student, first step we need to write to find maximum number of columns. To find, let's start. To find the maximum number of columns. Find the maximum number of columns, we have to find the SCF of, okay, please keep this in mind. We have to find the SCF of which two number we are given. First is 616 and 13. So, dear students, how to work out for that? As we know very well, First of all, 616. Let's divide. This is the bigger than 32, so we are going to divide it by 30. As we know, dear students, 32 ones are 32. There is minus. So if I subtract, then 23 will be left, right? 20, not 22 here, it is 11 minus 2 will be 9. 29 will be left, and let me bring this 6 down. Okay. Now 32 which number nearest if I do? Now 32 9 I know that is 280. Right? So if I subtract again from this 296 minus 288, then I will have here 2. Okay. So here the remainder is 2. Yes. Now one more thing we need to do here. These are actually we would like to say that is 660 equal to 32 into 19 and plus 4 remainder. Agree? 616 can be written as 32 into 19 plus 2. Get it? Now dear students, here whatever the value of this portion we are gaining 32, this is the number, that is a divisor. What we have to do, one more step we need to do here, that is divide 32 with the remainder. Divisor we are dividing with remainder. So 32 is divisible by 8, you know. If I divide 32 by 8, then I will have here 4. You know, 8 4s are 32. So dear student, this is also very important step. So in the next step, whatever the divisor is coming here, I need to mention it here. 32 equal to 8 into 4. And this time remainder is 0. So the SACDEV of these two numbers, this and this, SACDEV of this and this is 2. So final answer we are writing. Wait for a while. These two important steps we need to mention here. This is equal. Okay, this is how to write in a division lemma. Okay, let's write the final answer. So next step. Therefore, the SACDEV of these two numbers we were finding for 616 30. What it is coming? That is 8. SACDEV of this is coming 8. So final answer we need to say hence maximum number of columns. Hence maximum number of columns is. So the maximum number of columns, that is 8. This is a required result because we are want to find the number of columns, so that is 8. Question number 4 of exercise 1.1. The question is on your screen. Use Euclid's division lemma to show that the square of any positive integer is either of the form Pm or Pm plus 1 for some integer n. So yes, let's begin. Here we need to apply Euclid's division lemma. So let's start the solution. We are considering x. So we will assume let x be any integer. Let x be any integer. Then it is in the form of. Then it is in the form of, according to the question, that is the form of the x It can be in PQ, that can be in PQ form, that is PQ plus 1 or PQ plus 2. So we have to do next step. Form of X can be PQ plus 1 or PQ plus 2. We have to prove that what we have to prove? We have to prove that the square of each of the square of each of these. Square of each of these can be written in the form. We need to find the square. It can be written in the form Pm or Pm plus 1. Please keep this in mind. What we are assuming first? We are assuming X like it is an integer. Okay? It is in the form, so it can be in form of PQ plus 1 or PQ plus 2 according to the lemma. We have to prove that the square of each of these can be written in the form 3m and 3m or 3m plus 1. Okay, now we need to find the square of these two numbers. Let's see how to do. So dear students, next step, the square of 3. Of course, we know it can be 9q square. So we write 9q square as 3 and in bracket q square by separating it. So I am writing it here in this way. It can be written as 9 can be split as 3 into 3. So why I have done this? Actually we know q square equal to m. So this will become 3m because we know here the value of m is equal to 3q square. This is the value. Now one more step with us, that is 6q plus 1. Let's find its the square. As we know that 6q plus 1 whole square, we need to apply the identity. Which identity? A square plus 2ab plus b square. Okay. So my dear students, here it will be 3q, that is 3q, that is 1, and this is also fine. So dear students, can I write the 3q whole square is, you know very well, I am taking out this from these two terms. This I am keeping separate. Okay. First of all, we know 9q square plus 6q plus 1. 2 3 6q plus 1. This is the perfect square. Now can I write such a way? First two terms. From first two terms, something can be common. You can see from first two terms, 3 can be common. So we will have here 2 square plus 2 left and this is 1. 2 can also be taken out common. But here we need not have to go with that because just behind that this will be again the value of m. Okay. So dear friend, this will be the value of m because we want to bring them in 3m plus 1 form. So this is 3m plus 1. Where? What we can say? What is the value of m? Here m equal to value of m is this. 2 square. So we have successfully found it for first 3q. Then we have found it for 3q plus 1 whole square. Now we have to find it for 3q plus 2 whole square. Okay, so let's work out upon that. Now dear student, we will find 3q plus 2 whole square. We know again apply the square identity, a square plus 2ab plus b square. What is a here? 3q. What is b? That is 2. So dear student, what is 3q whole square? It will be 9q square. 3 2 ja 6 2 ja 12q plus 2 square, it will be 4. Fine. So as we did in the previous time, here also we are separating this way. Okay, here there is the technique which we have to apply. Okay, so what I am going to do here, 9q square plus 12q plus 3 plus 1, right? This 4, it indicates that 3 plus 1. Fine. So dear student, here 9q square plus 12q plus 4. That 4 I am separating as 3 plus 1. Now what I am going to do, I am taking out 3 common from this. If I take out 3 common, then I will have here 3q square, 4 3 are 12, here it will be 1 and this is 1. This is again in the 3m plus 1. Okay, why? Because we want to bring all the way in 3m plus 1 form. So again it is 3m plus 1. What is the value for m here? Where m equal to the value of m, what we are gaining? This is the value of m, 3q square plus 4q plus 1. This is the value of m. Got it? And this is the result. Hence the result. This is the result. So question 5 of exercise 1.1 on your screen. The question is, use Euclid's division lemma to show that the cube of any positive integer is either of the form 9q, 9q plus 1 or 9q plus 8. Okay, so again the same thing we are going to do here. Let x be an positive integer. Let's begin. Let x be a positive integer. Fine. Now it can be in the form. What can be its form? It is of the form. If it is positive integer, then what can be its form? Of course, we know that its form can be 3m plus 1 or 3m plus 2. It can be 3m plus 1 or 3m plus 2. This can be its form. Here we have to prove that. What we have to prove now? Let's note down. We have to prove that the cube of, now we have to go with the cube identity. Okay, cube of each of this, cube of each of this can be in the form, can be written in the form, which form we can write? They are given in the question. It can be in 9q form, or it can be 9q plus 1 form, or 9q plus 8 in this form. Okay, this we are already given. So the general form is 3m, 3m plus 1 and 3m plus 2. Okay, but here according to that they are asking we need to write in a cube of these so that it should be in this form. Fine, this we have to prove. Let's begin. So, dear student, according to that 3m whole cube we know that is 27m. Okay, 27m cube. Can I write this as a 9? 9 3 are 27 and here 3m cube. 9 into 3m cube. So that can be written as 3q. This is 9q. In place of that I am writing 9q. What is the value of q here? Where the value of q is 3mq. This is already with us. The value of q equal to 3mq. The same procedure we are going to apply the cube identity for 3m plus 1. As we know, the 3m plus 1 whole cube is a cube plus 3 into a into b, a square. 3a square b plus 3ab square plus big Q. This is the cube identity. Again I am repeating here. A cube plus 3a square b plus 3ab square plus big Q. What is a? That is 3m. Here also 3m. This is 1, 3m, 1 and this one. If we simplify this, then what do we have? 27m cube plus, here 3m whole square is 9m square. 9m square, 9 3 are 27m square. Again 3 into 3, 3 3 are 9m. 1 cube is 1. So my dear student, here I am going to take out 9 common from these 3 terms. So what do I have left? m cube plus m square plus m plus 1. So can I write it here? 9q plus 1. What is the value of q here? So dear student, here 9q plus 1. Where? What is the value of q here? You can see that is this much is term 3m cube plus 3m square plus m. Here. Now this we have found it for 3m whole cube and 3m plus 1 whole cube. Okay. Now we have to work out on 3m plus 2 whole cube. Okay. Let's see how to solve that. So dear student, let's work out on the last now, that is 3m plus 2 whole cube. Fine. So here a cube plus 3a square b plus 3ab square plus b. This is the identity. Now in that we know the value of a is 3m. This is also 3m. This is 2. The value of b is 2. Clear? So if I simplify it, then I will have here 27m cube plus, as you know, 3m whole square is 9m square. 9 into 3 into 2. It is 54. 54m square. Agree? Fine. Same thing is here. What is the square of 2? That is 4. 4 into 3 into 3. That is 36. And what about 2 cube? We know that is 8. So dear student, out of these first 3 terms, I am taking out 9 common. Then what will be left? If I take out 9 common, 9 3 are 27. 9 6 are 54 and 9 4 are 36. So this will be left. Now you can see we can compare it with this 9q plus 8. Okay, that is equal to 9q, this is q, plus 8. Now what is the value of q here? The value of q will be 3mq plus 6m square plus 4m. This is the required value. So you can see we have proved all the way 3m whole cube, 3m plus 1 whole cube and 3m plus 2 whole cube. All the way they can be equal to in the form. This integer can be written in the form 9q, 9q plus 1 and 9q plus 8. So this is the completion of exercise 1.1. So it's the time to update. Dear student, be ready for exercise 1.2. That is in upcoming video, which is quite easy and very interesting exercise. All these sums are based on your 5th and 6th class SCF LCM. So be ready. Thank you for watching the video and subscribing the channel. God bless you.